All right, welcome to another deep dive. We're tackling a pretty fundamental concept today, one that underpins a lot of engineering and physics: equilibrium. Specifically, we're focusing on the equilibrium of particles.
Yeah, it might sound a bit basic at first. Particles, tiny things.
Right, like dust motes or something.
Exactly. But the principles behind how these tiny things stay balanced actually apply to all sorts of objects, even really big ones.
Yeah, it's kind of mind-blowing when you think about it. Like, the same rules that govern a speck of dust also apply to, say, a giant skyscraper or a satellite in orbit.
Absolutely. It all comes down to forces and how they interact.
We've been digging through some of the core texts on statics, and we're going to try and break down this whole idea of equilibrium for you.
Yep, and hopefully by the end of this, you'll have a much clearer picture of what it means for something to be in equilibrium and why it matters.
So let's jump right in. Now, when we talk about equilibrium in engineering, we often start by looking at something called rigid bodies.
Right, and by body, we just mean the object we're focusing on. Could be anything, really.
Like if you're designing a bridge, the whole bridge could be considered a body. Or you could zoom in and just look at one of the supporting cables as a separate body.
Exactly. And then we have this concept of a rigid body. It's a bit of a simplification, but a really useful one.
How so?
Well, we assume that a rigid body doesn't deform under load.
hmm
Like it doesn't bend, stretch, or twist when forces are applied to it.
Okay, but in reality, things do deform, right? Even a little bit.
Of course, in the real world, nothing is perfectly rigid. Everything has some give. But by assuming rigidity, it allows us to make some really powerful calculations and understand the big picture of how forces are acting.
Sort of like a first approximation before you get into the nitty-gritty details.
Exactly. And those details, the ones about how materials actually deform under stress, those are covered in other areas of engineering, like strength of materials.
Makes sense. So we've got these rigid bodies. Now, what about this idea of equilibrium? What does that actually mean in plain English?
Basically, equilibrium means that something isn't accelerating. Remember, acceleration is just a change in velocity.
Right, so if something's in equilibrium, it's either completely at rest or it's moving at a constant speed in a straight line.
Exactly. No speeding up, no slowing down, no changing direction.
Now, I remember from physics that there's that famous equation, Faf-ma, that A is for acceleration.
Right. And in the case of static equilibrium, where things are at rest, the acceleration is zero.
So that whole ma part of the equation disappears, and we're left with Faf equals zero.
Precisely. That no just means the sum of, so basically the sum of all the forces acting on a body in equilibrium must equal zero.
Meaning all the forces are perfectly balanced, they cancel each other out.
Exactly. And here's a really important point. We can use this equation, F equals zero, in two ways. First, if we know all of the forces acting on an object and they add up to zero, we know that object is in equilibrium. It's not going to move.
Okay, that makes sense. What's the other way we can use it?
We can use it in reverse. If we know an object is in equilibrium, like we can see it's not moving or collapsing, then we know that all the forces acting on it must be adding up to zero.
Ah, so we can use that knowledge to figure out unknown forces.
Exactly. Like if we know the weight of a bridge and we know it's not falling down, we can use zero equals Néron-Wayhue to calculate the forces in the cables that are holding it up.
That's pretty neat, but it's not as simple as just adding up numbers, right? Because forces have direction.
Absolutely. We're dealing with vectors here, not just plain numbers. When we say 0 vio 0, we're talking about vector addition. You have to take into account both the magnitude of the force, how strong it is, and its direction.
So it's not just about how hard you push or pull, but also which way you're pushing or pulling.
Precisely. You might have to break down the forces into their horizontal and vertical components, making sure those components balance out separately.
It's starting to sound a bit more complex than just adding and subtracting.
Well, it can get a bit involved, especially as we move into more dimensions. But the core principle remains the same. For a body to be in equilibrium, all the forces have to balance out.
You mentioned that Fufdeno is a really big idea in statics. Is there another one we should keep in mind?
Yeah, later on, when we start dealing with objects that can rotate, we'll introduce another important equation, phi equals 0. That m stands for moment, or torque. It's basically a measure of the twisting force that can cause rotation.
Okay, so we'll have to remember that for later. But for today's focus on particles, we're just sticking with Fuf-de-Zero.
That's right, because when we're dealing with particles, we're assuming that all the forces are acting at a single point, or at least along the same line.
Yeah.
So there's no rotation to worry about.
Okay, that makes sense. But speaking of particles, when I hear that word, I tend to think of something really, really small, like a tiny speck of dust. Is that what we're actually talking about here?
That's a common misconception. In engineering statics, a particle isn't defined by its size, but by how the forces are acting on it.
So it's more about the arrangement of the forces.
Exactly. A particle is any object where all the forces acting on it either meet at a single point or act along the same line.
So even something large could be considered a particle in certain situations.
Absolutely. Like imagine a satellite orbiting the Earth. If we're just analyzing its orbital motion, we can treat both the satellite and the Earth as particles, with the gravitational force acting between their centers.
So the Earth, a giant planet, can be thought of as a tiny particle in that context.
Exactly. It's all about simplification and focusing on the relevant forces. But of course, if we were designing the satellite itself, we'd have to consider its individual components as separate bodies, not just a single particle.
So the key is whether or not the forces are causing rotation.
Right. For a true particle, the forces either all act at the same point or they all act along the same line. So they can't cause any twisting or spinning.
Okay, I think I'm starting to get it. So if all the forces are acting at a single point or along the same line, how does that simplify things for us?
It simplifies things a lot because it means we only have to worry about the object moving from one place to another, what we call translational motion. We don't have to worry about any rotational motion.
That's why, for particles, Phi-Phi-O-Vero is the only equilibrium equation we need.
Precise.
But even with that simplification, there are still limits to what we can solve for, right?
That's right. Each equation gives us a certain amount of information. In two dimensions, for instance, Phi-Pho-V actually breaks down into two separate equations.
Because we have to consider both the horizontal and vertical directions.
Exactly. So we have Phi-Phi-Phi is 0, meaning the sum of the forces in the x direction must be 0, and Phi-Phi 0, meaning the sum of the forces in the a direction must be 0.
So we have two equations, which means we can solve for a maximum of two unknowns.
Precisely. Those unknowns could be the magnitudes of two forces, or the magnitude and direction of a single force, or some other combination. But if you find yourself with more than two unknowns in a 2D particle problem, you'll need to find some additional information or take a different approach.
Okay, that makes sense. Now, you also mentioned that we often treat forces as concentrated forces. Can you explain what you mean by that?
Sure. In reality, forces are often distributed over an area. Like, gravity pulls down on every single part of an object.
Right, not just at one single point.
Exactly. But to make the math easier, we often represent that entire gravitational force as a single force acting at the object's center of gravity.
So it's like we're assuming all the weight is concentrated at that one point.
Precisely. And for many practical purposes, that's a very accurate approximation. It's similar to how we often treat the Earth as a point mass when calculating its orbit around the Sun. We know the Earth isn't really a point, but it simplifies the calculations and gives us a pretty accurate result.
So it's all about making the math more manageable without sacrificing too much accuracy.
Exactly.
Okay, so now that we've got a basic understanding of particles and equilibrium, let's get into some examples. Let's start with the simplest scenario. One-dimensional equilibrium. You mentioned something about a weight hanging from a rope earlier.
Yeah, that's a classic example. Imagine a light bulb hanging from the ceiling by a single wire.
All right, I can picture that.
Now, in this case, we can treat the light bulb as a particle because all the forces acting on it are along the same vertical line. We have the tension in the wire pulling it up and the weight of the light bulb pulling it down.
So how do we analyze the forces in this situation?
We use something called a free body diagram. It's a really crucial tool in statics.
What exactly is a free body diagram?
It's basically a simplified drawing where we isolate the object we're interested in this case, the light bulb, and we show only the forces that are acting directly on it.
So we ignore things like the ceiling and the wire itself.
Right, we only focus on the forces that are directly affecting the object we're analyzing.
Okay, so for our hanging light bulb, what would the free body diagram look like?
It'd be pretty simple. You draw a dot to represent the light bulb. Then you draw an arrow pointing up from the dot to represent the tension in the wire. Let's call that tension T. And then you draw another arrow pointing down from the dot to represent the weight of the light bulb. We can call that W.
And those are the only two forces we need to worry about.
Right. Those are the only external forces acting directly on the light bulb.
And since the light bulb is just hanging there, not moving up or down, we know it's in equilibrium.
Exactly. So we can apply our equilibrium equation, phi equals 0.
But in this case, it's one-dimensional, so it's just 5 equals 0,
Yeah.
right? Since all the forces are vertical.
Exactly. If we take upwards as the positive direction, our equation becomes TW equals 0. We make the weight negative because it's acting downwards.
So that tells us that the tension in the wire, T, must be equal to the weight of the light bulb, W.
Precisely. So if we know the weight of the bulb, we automatically know the tension in the wire. Or, if we know the maximum tension the wire can handle, we can calculate the maximum weight the bulb can have before the wire breaks.
So this simple example shows how we can use the idea of equilibrium to solve real-world problems.
Absolutely. And it highlights the basic principle. For a particle in equilibrium in one dimension, the forces acting in one direction must be equal in magnitude and opposite in direction to the forces acting in the other direction.
That makes sense. You mentioned two force bodies earlier. Is our hanging light bulb an example of that?
Yes, it is. A two-force body is any object that has only two forces acting on it. And for it to be in equilibrium, those two forces have to meet a few conditions.
What are those conditions?
First, they have to have the same magnitude, meaning they're equally strong. Second, they have to act in opposite directions. And third, they have to act along the same line.
Our light bulb example fits all those conditions, right? The tension and the weight are equal, opposite, and act along the same vertical line.
Exactly. And you see two-force bodies all the time in engineering. Like, think of the struts in a truss bridge or the connecting rods in an engine.
And sometimes we ignore the weight of these two force bodies.
Right. If the weight of the object is very small compared to the other two forces, we can often ignore it for simplicity. Like if the cable holding up a heavy weight is very light, we might ignore the cable's own weight in our calculations.
So it's a way to simplify things without losing too much accuracy.
Exactly. But if the weight is significant, then we have to include it, and it becomes a three-force body, which makes the analysis a bit more complex.
Makes sense. Now, you also talked about the center of gravity. How does that play into all of this?
Well, for a simple object like our light bulb, we can assume that its entire weight acts at a single point, which we call the center of gravity. It's basically the balancing point of the object.
So if we were to suspend the light bulb from its center of gravity, it would hang perfectly straight.
Exactly. And the line of action and the tension in the wire would pass directly through the center of gravity, ensuring that there's no tendency for the bulb to rotate. But if you were to try and suspend it from a point that's not its center of gravity, it would likely start to rotate until its center of gravity was directly below the point of suspension.
Okay, so the center of gravity is important for understanding how an object will behave when suspended or supported.
Exactly.
You mentioned a tug-of-war example earlier. Can you explain how equilibrium applies in that scenario?
Sure. In a tug-of-war, if the rope isn't moving, the entire system is in equilibrium. Each team is pulling on the rope with a certain force, but those forces are balanced, so the rope stays still.
So if one team pulls with, say, 1,000 newtons to the left, and the other team pulls with 1,000 newtons to the right, the net force on the rope is 0, and it stays in equilibrium.
Exactly. And it's interesting to think about the tension in the rope itself. If you imagine cutting the rope in half, you'd see that there's an internal tension force of 1,000 newtons pulling in both directions.
So each team is essentially balancing out that internal tension force.
Precisely. And that's what allows the rope to stay taut and not snap.
Okay, I think I'm starting to see how equilibrium plays out in the real world. So we've covered one-dimensional equilibrium. What about the general process for tackling these problems and for moving into more dimensions?
Well, the approach is generally the same, no matter how many dimensions we're dealing with. The first step is always to draw a clear, free body diagram of the particle we're analyzing.
Showing all the forces acting on it and only those forces.
Right. Then we need to choose a convenient coordinate system, like the XY axis.
To help us keep track of the directions.
Exactly. Then we apply the equilibrium equations. In 1D, that's just a phi A, those are vertical forces, or phi x equals 0 for horizontal forces.
And we solve those equations for any unknown forces or angles.
Precisely. And finally, it's always a good idea to check our answer and make sure it makes sense in the context of the problem. Like, does the direction of the force seem reasonable, and does the magnitude of the force seem plausible?
Okay, that makes sense. Now, when we step up to 2 dimensions, 2D particle equilibrium, what new challenges do we face?
The main difference is that now forces can act at angles.
So it's not just up and down or left and right anymore.
Exactly. So our single vector equation, side A airs, actually breaks down into 2 separate scalar equations.
Because we have to consider both the horizontal and vertical components of each force.
Precisely. So we have Ceph x 0, meaning the sum of the horizontal components of all the forces must be 0.
And Pfeffis equals 0, meaning the sum of the vertical components of all the forces must be 0.
Exactly. And to apply these equations, we often have to break down forces that are acting at an angle into their horizontal and vertical components.
So if a force is pulling upwards and to the right, we need to figure out how much of that pull is acting horizontally and how much is acting vertically.
Right. And we can use trigonometry to do that.
Yeah.
If we know the angle of the force and its magnitude, we can calculate its horizontal and vertical components using sine and cosine.
And just like in 1D, the number of unknowns we can solve for is limited by the number of equations we have.
Exactly. In 2D particle equilibrium, we have two independent equations, so we can typically solve for, at most, two unknowns.
Those unknowns could be the magnitudes of two forces, the magnitude and direction of a single force, or some other combination. Now, you briefly mention a force triangle method for 2D equilibrium. What is that and when is it useful?
It's a really neat trick that we can use when we have exactly three forces acting on a particle in equilibrium. The idea is that since the forces are balanced, if you were to draw them as vectors and arrange them tip to tail, they would form a closed triangle.
Ah, so the three forces would basically cancel each other out visually.
Exactly. And we can use this geometric representation to solve for unknown magnitudes or angles within the triangle using trigonometry, like the law of sines and the law of cosines.
So it's a more visual approach that can sometimes be quicker than breaking down all the forces into their components.
Right. It's a good option when you only have three forces to deal with.
You also mentioned the scalar components method for 2D equilibrium. Is that just an extension of what we saw in 1D?
Basically, yeah. We're still using a for 0, but in 2D it becomes Fes I plus Fx ij equals 0.
Where I and j represent the unit vectors in the x and y directions.
Exactly. And this equation basically tells us that both the horizontal and vertical components of the resultant force must be 0. That's why we get our two scalar equations. Fx equals 0 and Fx is 0.
And this method is more general. It works for any number of forces.
Right. It's the most widely applicable method for solving 2D particle equilibrium problems.
Okay, that makes sense. Now, what about when we have multiple particles interacting with each other? How do we handle that?
That's when things get really interesting. The key is to remember Newton's third law. For every action, there's an equal and opposite reaction.
So if one particle pushes on another, the second particle pushes back with the same force in the opposite direction.
Exactly. And those forces are called action-reaction pairs. So when we have multiple particles in equilibrium, we have to analyze each particle separately, drawing a free body diagram for each one. But we also have to remember that the forces they exert on each other are linked.
So if we know the force that particle A exerts on particle B, we automatically know the force that particle B exerts on particle A.
Precisely. And we can use those relationships to connect the equilibrium equations for the different particles, allowing us to solve for unknowns in the entire system.
So it becomes a bit like a puzzle, where we have to piece together information from different parts of the system.
Exactly. It can get a bit tricky, but it's also really fascinating how everything connects together.
And then we can take the ultimate leap into the real world, three-dimensional particle equilibrium.
Yeah, that's where things get really challenging in terms of visualization and the math involved.
So now we're dealing with forces that can act in any direction, not just within a plane.
Right. Our basic principle, phi L0, still holds, but now it breaks down into three scalar equations. Fx equals 0, Φ equals 0 and Fs equals 0.
So now we have to keep track of three components for each force.
Exactly. And we often have to use more advanced techniques like direction cosines to describe the direction of each force in three-dimensional space.
Sounds pretty complicated.
It definitely requires more careful attention to detail and a good grasp of spatial reasoning.
Well, I think that was a fantastic overview of particle equilibrium. We covered a lot of ground, from the basics of one dimension to the complexities of three dimensions.
Yeah, we went through quite a bit.
So just to recap, the main idea is that for a particle to be in equilibrium, the vector sum of all the forces acting on it must be 0.
Right. It's all about balance.
We learned about free body diagrams, which are essential for visualizing and analyzing the forces.
And we saw how this concept of equilibrium applies to all sorts of objects, from tiny particles to giant structures.
And even though it can get complicated, the core principle is surprisingly simple and elegant.
Yeah, it's really quite amazing how such a simple idea can have such wide-reaching applications.
So next time you see something that's just sitting there seemingly motionless, remember that there are actually a bunch of forces acting on it, all perfectly balanced to keep it in equilibrium.
It's a hidden world of forces, constantly at play all around us.
Thanks for joining us on this deep dive into particle equilibrium. We hope you learned something new and interesting. And as always, keep exploring and keep asking questions.